Hey, thank you. I hope in the next few minutes to show you some of the exciting problems that we get to work on in the impact mechanics field and convey some of the methods that we use to understand what happens in really fast, dynamic, and typically destructive events. Initially, I'd like to say thanks to a number of long-term colleagues, one of whom, Charles Anderson, is here today, so thanks working with him, and also my primary sponsors have been the Department of Defense, NASA, various commercial firms, and also Southwest Research's internal research program. I work at Southwest Research Institute, which is an independent nonprofit R&D center. We live entirely on contract research. We don't have any endowment or any assured tax base. We sign contracts with our clients and in return deliver research. So we have about 50% of our contracts are with industry, 50% are with government. People come to us when they feel we have the expertise to solve their problem. So what do we mean by impact? Well, it's not number of journal citations. It's what we mean is the physical collision of two bodies, and it can happen at a wide range of speed. We've studied everything from pebbles hitting cars and chipping car paint all the way to the current Cassini spacecraft flybys of the moon Enceladus, which have been occurring at about 40,000 miles per hour, looking at ice grain impacts in their mass spectrometer. And historically, the field includes all forms of dynamic loading, including those caused by explosions and explosives. We use a three-pronged approach: experiments, large-scale numerical simulations, and analytical modeling. Analytical modeling is where you make a number of physical assumptions and typically symmetry assumptions about the geometry and are able to reduce the problem down to a small number of ordinary differential equations that you can rapidly solve. Along with these, and behind all of them, is very important the material characterization and modeling part. Our numerical simulations aren't very good if we don't have very good numerical models, so a lot of our experiments are aimed at getting material information and how to actually model it, and then applying those in our calculational techniques. So impact studies usually relate to safety, survivability, and risk. We ask questions or answer questions. How dangerous is the impact event? What kind of protection is needed for a person to survive the event? And what is the overall risk of the impact event? And I'd like to give you a sense of how we go about things with 4 specific examples and then a coda. We're going to look at the Space Shuttle Columbia accident, military ground vehicles and improvised explosive devices, the new Navy destroyer, the U.S.S. Zumwalt, and then the International Space Station, and then the coda at the end on deflecting asteroids. On February 1st, 2003, the Space Shuttle Columbia disintegrated on re-entry, resulting in the death of all 7 crew members. So the problem, what was the cause? We were approached because of our expertise in impact, because one of the early proposed causes was that the accident was due to insulating foam strike that occurred during liftoff. At about 82 seconds into flight, a piece of foam broke away from where the shuttle connects to the external tank, and it traveled the 58 feet to the leading edge of the wing in 0.16 seconds and struck with a relative velocity of about 530 miles per hour. This piece of foam was about 1.5 pounds in weight. Possible foam impact locations, you just saw a video, but we're on the underside of the wing or perhaps on the leading edge itself. The underside is covered with the famous thermal tiles, the leading edge with a different material, a reinforced carbon-carbon material. The very first thing we did was get material properties. We had to get properties that hadn't been gathered before, such as we did materials tests to crush up the foam. We did it so we got large deformation information. We got high rate information. The material does behave differently at high rates. And we also looked at the crushing failure behavior of the tile. And this information then we combined to put into material models that then were coded up and put in our software tools for impact. And here you can see a short video of one of those where we have a 1-inch cube of foam striking a thermal tile. And also developed, as I mentioned, were fast-running analytic models. Well, what these led to was, for the first half of the investigation, the focus was on the thermal tile region, and we developed the chart that you can see here where we have, this is impact speed, impact angle, so tiles above this line, this damaged, no damage demarcation curve, were damaged. Below this line, they weren't damaged. So for high speeds but shallow angles, no damage. Slow speeds but normal angles, they were damaged. So the question then became, so where was the foam strike on the Columbia during ascent? And it was in this region down here below the damage, no damage transition curve. So in fact, an impact of the foam on the thermal tiles was not the cause of the Columbia accident, mostly because that impact would have had to be quite steep angle during the ascent. So then the focus of the investigation shifted to the leading edge itself, which is made of a different material, as mentioned, the RCC material. So a part of the wing was built, and panels were taken off existing shuttles to have similar lives and similar experiences for the materials. We took it to our outdoor ranges where we have large compressed gas guns, and at the same time we were working on material models where here's showing a computation of a foam striking a panel where we're looking at the stresses in the panel. So we could explore things such as what's the best impact angle and arrangement to match what we think were the conditions during the impact of during the shuttle ascent, and also to look at the sensitivity to impact point. We also did experimental tests. Interesting thing about impact tests is you have to get it right the first time, especially when you have parts you can't replace. So we have lots of instrumentation. We have up to 16 cameras, high-speed video cameras in this case, up to 250 channels of data that we're collecting, and then we perform the test, and we'll show you some video of the test here. This is a real-time video.
1, 0.
So this confirmed that a foam strike could cause a lot of damage to the thermal protection system, the leading edge component here. And here's a couple images of the high-speed video. So you'll notice that the foam, as it comes in, it's quite compliant. The panel is fracturing behind that, and then we catch and start breaking apart the foam. And seen from another angle, the same test, this impact is on a panel that had flown on Atlantis. You can see the RCC material is quite brittle, and this is a structural failure of the thermal protection system. Well, this led to the strong conclusion of the Columbia Accident Investigation Board that the physical cause of the loss of Columbia and its crew was a breach in the thermal protection system, which was caused by the foam strike on ascent. Well, this led to some other work because we wanted to continue flying the space shuttles, namely what was the risk, and we developed models that then were exercised literally millions of times in doing risk assessments before the shuttle flew again. And we also were asked questions, what are ways to ascertain damage? So one thing they did is now they photographed the shuttle going up and on orbit, but we also developed a wing leading edge impact detector system with accelerometers placed within the wing. And if we could play a video. So the clips you hear are foam strikes. So those are foam strikes on the way up. So we were able to detect impacts, and that was one way to look at damage both on orbit as well as during ascent. Second example, military ground vehicles and improvised explosive devices. So in our operations in Afghanistan and Iraq, our ground combat vehicles are often attacked, typically with buried explosives. So the problem, to protect the crews and improve the survivability of the vehicles. We also had the problem of we need to reduce the development time so we can get stuff into the field more quickly to be more responsive. So there were a number of solutions that have come out of that. Survivability tools to aid in the design and analysis of new vehicles and armors. Show some examples of multi-fidelity modeling tools to allow rapid exploration of the design space, as well as numerical tools that do the analysis directly from CAD. And examples I'm going to show are taken from the Defense Advanced Research Projects Agency, DARPA, Adaptive Vehicle Make program, in which I'm a principal investigator. So these are examples. On the left here, you can see one of the analytic models that I described, which this one of those happy things in history, developed many years ago, but now it bears Charlie Anderson and my names. So it had pretty innovative methods for computing resistance. So that's a fast-running model. And then we also have a more complicated model that's slower running, but you would use when you get to the more higher fidelity design process as you're refining your design. So by having fast-running models juxtaposed with the higher fidelity models, you can more rapidly explore the design space as then you start focusing in on your design. We also have this for blast. This is a rapidly running blast loading model. An important part of this is getting good blast loads. So we do blasting tests where we're throwing debris and soil from explosives into flat plates, angled plates, to get a quantification of what the loads are that then apply to the vehicle structures. Right now you're watching some video that's shot at about 20,000 frames per second. The Shuttle video was shot at about 7,000 frames per second. If you like the movies, that's shot at 24 frames per second. But of course we even have faster cameras. Camera technology is an important part of the impact world. When I first started in the field, one of the first things you'd hear during a test was the zzz, as the celluloid film cameras came up to speed, so they could be running the film through the camera fast enough so you could have high-speed film. Now we have all electronic cameras. This is an example of a setup where we're doing a flyer plate impact test, where our exposure time was 5 nanoseconds, and the frames are 200 nanoseconds apart. So to get enough light in there, we need lasers. Whenever you have impact of consolidated material, you have bright flashes, so we need to include filters to remove the flash. What other things are we doing to speed up the design and development time? And as I mentioned, we're automeshing directly from CAD. So this is an example of a vehicle design, again from the DARPA program, where we're taking the CAD files and there we're automeshing them directly, and then we can load those into our analysis tools. Here's an example of the analysis tools. We see a blast, underbody blast on this vehicle design and on this different vehicle design. And finally, we can look at stresses, and as you get it to the higher fidelities of our models, we also include dummies, so we can look at injuries to spine, the neck, and also to the shins. A third example, rather innovative approach to magazines was proposed for the DDX destroyer, which is now called the Zumwalt class destroyer, and magazines are where the missiles are stored. And in theory, they'd produce a much more survivable ship, one that could survive advanced threats as well as work closer to shore. So a big problem and a general principle in impact mechanics is that impact events do not scale. And as you go to larger scales, it always is to the benefit of the offense. So the problem is that a full-scale magazine test with missiles in it and everything is incredibly expensive, and only 2 were performed during the design process. So we have to develop a design tool so computationally we can design the majority of the ship, since there are multiple magazines on the ship, and they have different shapes and different locations. So that's what we did. And this computational tool is a multi-method analysis tool. And by that I mean, for the actual explosion and gaseous expansion of the explosive products, there are certain tools that work very well. For the structural deformation, there are other tools, other numerical methods that work very well. And we had to link those together, passing the information so that we could pass dynamic loads to the structural calculations, and so we could then solve the large-scale fluid structure interaction problem for the ship design. And this method went under a pretty intense verification, validation, and accreditation program since it was used in the ship design process. We do this same kind of thing, if I can make an aside, for other projects that we do. So for example, we've proposed a asteroid seismology mission, and we do calculations of the blast in a small scale, just 1 meter scale. And then if you're looking at a large asteroid, and as an example here is Eris, you're at many kilometers scale. So we do where the blast calculation is performed best in one tool, and then we transfer those loads to where the wave propagation is performed best in another tool. Here's some Navy footage of one of the magazine tests I described, where you can see the interior is being detonated. And this is a pretty violent event, and you'll see there's a venting region which is intended to vent, but on the other side, there's not much deformation. And in fact, not only is the ship survivable after this event, but it's still operational. So this was a very successful design. And one of the gratifications in working on a big program like this is that last October, the ship was launched. So this is some time-lapse photography from Bath Iron Works up in Maine, where the first destroyer of this class, the Zumwalt, was launched. As a fourth example, I'd like to talk about the International Space Station, which resides in low Earth orbit. It's going at over 7.5 kilometers per second. And there's orbital debris up there, which is stuff left over from previous flights, which can have relative speeds of 0 to 15 kilometers per second. We can't have the crew module perforated, and traditional launcher technology can only get up to about 8 kilometers per second. So we need to get to higher speeds in order to validate the protection design. And a solution that we were involved in was that at Southwest we designed an explosive launcher that will launch over 10 kilometers per second to examine, in particular, it was to examine, excuse me, did I do something wrong? To examine the shielding on the International Space Station. So if you look at traditional launcher technology, can someone help me with the slides? Did I do something? Thank you. So in traditional launcher technology, you have the gas guns like we used in the Columbia accident investigation, where you can go about the sound speed of the driving gas, about 300 meters per second for nitrogen, around a kilometer per second for hydrogen, and we do that. You also have powder guns, which can go up to about a kilometer per second for small ones, and large ones up to about 2 kilometers per second. There's some very specialties, two-stage light gas guns, which can get to about 8 kilometers per second, but unfortunately they launch very small projectiles. And so we developed here something that can launch in excess of 11 kilometers per second using explosive techniques. A shaped charge is a shape within an explosive, and here you can see an outside picture of one where we have the explosive is the brown material, and then we have this conical liner, it's called, on the inside. It's detonated at the end. When the detonation front reaches the liner, it collapses it and produces a long metal stretching jet. And this tip is traveling in excess of 11 kilometers per second. So it was suggested in the early 60s by some people, if we could isolate that tip, we could have a launcher. It took a lot of advancement in computational technology, though, to be able to do that. And so we finally got it to work in the early 90s and working on it for the specific space station application. Here's one of the design calculations from that time frame that I performed. So we have the detonation front reaching the liner. Then we placed an inhibitor on the inside of the liner here, which you can see will collapse down and pinch off the jet. And we only launched the jet tip, which again is in excess of 11 kilometers per second, about 25,000 miles per hour. This led to the design of a chamber. This is what it looks like, an evacuated chamber, so we can launch down here. We have flash X-rays, which are a big tool for us in the impact community. So when we detonate the explosive, the shielding is in there. You see flash X-rays of what this projectile looks like, and then that's what the shielding was validated against that is currently flying on the International Space Station. You might say, why can't you go faster? Why just 11 kilometers per second? And in fact, if you reduce the angle on that liner, you start getting faster jets. But what happens is they begin to radially expand, and they become useless as a projectile. During my calculations, I was never seeing what the traditional explanations of that effect were, because there were a number of explanations. And so in my looking at it, I realized that what was happening here was that it mattered as you exited the collapse region in that moving frame of reference. If your jet stayed below the pressure-dependent sound speed of the material, then you stayed coherent. You produced a nice projectile. If, though, you exceeded the sound speed in that region, then you would have this radial expansion. I presented this as a poster at a conference. It led to one of my most exciting times in my scientific career, which is why I'm mentioning it here. And I remember watching from a distance the current person at that time who had the reigning explanation for the cause in a pretty heated discussion with another of the longtime shaped charge people, Pierre Chanteray. Then, interestingly, 18 months later, I was at a conference where Chanteray gets up and starts describing some very clever experiments he was doing. And it suddenly struck me, wow, he's got a way to verify whether or not my explanation is correct. And he hadn't called me ahead of time, but yeah, we went 10 minutes into the talk as I'm getting more and more excited about, where are we going with this? Finally, he shows his results and said, and this is in conformity with the theory presented by Walker at the previous conference. So that was a pretty exciting moment for me. So finally, a coda on deflecting asteroids. You probably saw a video of what happened over Russia recently. So we may want to deflect an asteroid for planetary protection purposes, or we may want to move it for engineering or scientific purposes. And right now, the most developed way to do that, the most technologically ready way to do that, is by hitting it with a hypervelocity impactor. And most of the momentum transfer doesn't come from the impactor itself directly, but from debris that is thrown off by the impact. And so the question is, quantitatively, how effective is this at deflecting an asteroid? Remember, impacts don't scale, and another problem is you start going to higher velocities, your launch package gets smaller and smaller, so we really have kind of a problem. So I'm kind of just going to give you a vignette here of some possibilities. So we took and launched with one of our powder guns, which can get to 2 kilometers per second, a 125-gram sphere of aluminum into a big 1-meter sphere of granite. We did computations ahead of time, again, where you can see the way the waves rock. And can you click on the other one where you can see the damage that occurs inside the sphere and see, you know, we're not throwing away a lot of debris per se, but it's still a significant amount. And of course, with the experiment, these are some stills from the experiment because I'm going to show you a video, but it's going to happen very fast. Even though it's 6,000 frames a second, you're probably not going to see what happens at the beginning. But the projectile exits the gun barrel, and as the propellant gases vent around it, we see a lighting of the front end of the sphere. There you can barely see the projectile. Here you can see it. It's only in 2 frames. The vapor trail. We have the strike, and of course we have our impact flash I described, which saturates our images for about three frames here, and then we start seeing the ejecta thrown back. So here's the video. But the point is, a lot of ejecta is thrown back. So even though it's at a lower speed, most of the momentum transfer is coming from that ejecta that comes back. So how efficient can it be? Well, you have to extrapolate in 2 directions. You have to extrapolate up in speed, you have to extrapolate up in size, but if based on much smaller scale tests than this and this are taken into account, extrapolation for a 1-meter aluminum sphere striking rock at 10 kilometers per second shows a multiplier of 44 times on the amount of momentum that's transferred to that object. So it's actually quite a lot. The scaling up behavior presumably is due to fixed length and time scales in the rock damage processes. Does it saturate so we don't quite get there? Well, we'll only know by having more experiments. But one of the interesting things about the scale behavior is that impacting with 1 large impactor is better than impacting, say, with 10 small impactors that add up to the same mass. In fact, you can show that it's about 35% more efficient to strike with that larger impactor. In summary, we've looked at a few applications, but I hope you walk away with the overall picture that we bring tools of experiments, large-scale numerical simulations, and analytical modeling, and all of these combine to help us understand what occurs in these dynamic impact events. Thank you. Well, I think that would be addressed by if you look at what we're actually doing right now, and you'll find that most of our internal investment is on material models and improving material models. Because they're, in particular, some of the newer composite materials, they're very hard to model from an impact damage perspective.
Thank you very much.
Well, there's someone, I think, at the mic.
It's a little bit glib, but so in the last part you're talking about the asteroid impact, and you're saying it's more efficient to use one impact, but what if you miss?
Yeah, that's not a very efficient, yeah. Yeah, and admittedly, the other part of that is, what you probably want to do is have multiple impacts over time. You'd want to put a transponder on it so you can make sure that your deflection is going the way you want. And then you could make adjustments in case it was not.